Welcome to Ghosts in the Machine Learning. My name is Thomas LaRock, and with me today, Karlo Zatylny, a distinguished engineer here at SolarWinds.
Hey.
You can wave. Yeah. And also with me is Anthony Bartolo from Microsoft. He is a cloud advocate.
Cloud advocate.
All right. And your specialty, of course, is machine learning.
Machine learning, IoT, a little bit of security.
All right. So I believe that there's a little bit of confusion in the marketplace because a lot of times you hear tools are said to use the magic of AI in order to make everything better. But to me, there's a really big difference between things that are artificial intelligence, machine learning, which is a subset of artificial intelligence, and then deep learning, which is a subset of machine learning. I usually describe it, AI, as anything that a human would have done that can be replaced by a computer. I know that's a very general term, but that's usually the way I describe what could be AI, which can also just be a PowerShell script or rules-based recommendations. What would your definition of AI be?
It's interesting because in this day and age, people hear AI and say, if I just rub a little AI on my product, it'll be that much better. And the real definition of AI is discovering of patterns within the amount of data that's out there to really detect either a clustering or an anomaly, something that pertains to an opportunity or a problem, right? The whole aspect of machine learning isn't even new. It was established in 1954 in regards to the algorithms that were created, but it isn't until now that we actually have the compute cycles to automate a lot of the tasks that were done manually prior. So the big piece with this in terms of AI is what question or what opportunity are you trying to address in respect to the implementation of machine learning to have the outcome of AI or an automated response to whatever that may be, right?
So AI to you is a little bit more than just automation.
It's about learning, right? The whole aspect about learning about what the data actually means and what it's trying to tell you. And most times you don't even know the initial problem that you're addressing until you've chewed through the actual raw data itself.
And there has to be some intelligence behind it. So like a chatbot that just gives me automated responses?
Chatbot is nothing more than a framework that provides you an automated response to a question that you put forward. In the scenario of what we're going to be talking about today, understanding the data that's coming in from the raw data and coming out with a pattern that is addressable, right, in terms of an opportunity or problem down the road is something where the actual AI comes into play.
Okay. So Karlo, talk to me a little bit about how you would define machine learning.
So machine learning is the ability for us to actually set the parameters of an algorithm or a mathematical formula. What we need to do is look at the data, and we have an algorithm that we don't know what the input parameters are going to be. So by analyzing the data, we're able to have the machine tell us what are those proper input parameters, or what are the specific needs for the formula to actually operate to tell us what the results are.
And when we say that we've put machine learning inside of DPA, we're talking about actual math, right?
Yeah. So what we're doing there is we're saying, all right, we have time series data that we're trying to analyze, and we want to find anomalies in it. We want to reduce alerts for our users. So in order to achieve that goal, we need to learn what's normal and what would not be normal. And we don't know what those parameters are, or what the cycles or what the seasonalities are. So in order to do that, we need to throw a bunch of data and some data scientists at some algorithms and say, all right, what are the best algorithms for us to use, and what are the parameters on those algorithms in order for us to actually effectively detect the anomalies.
So do you think you could take a moment and maybe show us how the machine learning inside of DPA works?
Absolutely, I'd love to do some drawings.
Step in there.
So for DPA, what we did was we wanted to look at a bunch of data and find what are the general patterns inside of the wait time data that we're gathering from the database performance analyzer. So every database, when you run a query, it ends up having some wait time, and over time you end up with all of the wait time for the entire database, and we track that inside of DPA. And what we wanted to do was ultimately reduce the amount of alerts that somebody's having. So we started with that question, and we knew that we had this data, and we wanted the model to tell us what exactly the data looks like. So what we found out, and what the model ended up telling us, is that there's 3 general seasonalities to most people's data. First of all, there's an overall trend where the data is either trending up, trending down, sometimes it's flat, but in general, most people's data is just trending in some different way. Second, the model told us that there was 2 different seasonal components of the data, and that was our question: is how many seasons do people typically have, and then how frequent are those seasons? One season was, not surprisingly, a weekly seasonality, so 168 hours, and that pattern generally looks low on the weekends, higher during the weekdays, and then low again on the weekends. So in general, that's how most people's patterns go, but it differs and varies from database to database. Lastly, we found another seasonality, which again was not surprising. It's a 24-hour seasonality. Most people have the nightly database backup, which has a spike, and then it goes down, but then people come into work and they have another rise, and then people go home from work. So we ended up with a 24-hour trend as well. So by taking all of these individual pieces and rubbing them together, the machine said, this is what most people's data looks like. So anything that is different than this data is going to be anomalous. So in order to build in some fuzziness on top of this, what you do is you take all of this data, run it through these different seasonalities, subtract all of these seasonalities from the data, and you end up with residuals. And the residuals end up being centered around 0, and there's some basic white noise going on there. But you find the standard deviation of this data, and that gives you a nice little window around the seasonal components that then says, all right, here's your thresholds, and then you can be fuzzy based off of how many standard deviations you are away from the predicted value to say, how anomalous are you? And it's more of a mathematical, standard statistics sort of thing.
What's great is that you've actually split out your data inquiries in terms of your model to address the one opportunity in terms of what data is actually being passed through. It's not something where you've gone and just created this one monster model. You're actually taking the outcomes of each inquiry and having that process data as opposed to using the raw data to provide your final tally in terms of what your predictability is going to be. That's what we're now looking at in terms of like edge computing, where data is actually being captured at a source and the source is making the deduction for the output and then taking that process data to make the finalized output at the end to have better accuracy in terms of your predictability.
Yeah, it's been great because as we've seen in the field, as we go to actual customer data, that each individual component, although it's been defined at the 168 hours and the 24 hours of seasonality, is that still is able to be flavored by each individual component. And so even within the thousands of databases that our customers are monitoring, each one gets its own little flexibility to it. So even if your seasonality isn't exactly 24 hours or exactly 168 hours, it's close enough and the model adapts to it.
And it is the best practice that's recommended in terms of analyzing of your data, the raw data, as opposed to taking it all in one chunk from the raw and trying to have that predictability output. You actually uplift your reliability and credibility of your data at the end with the process data being funneled through as opposed to going with the raw at the start.
So as much as I love your drawings, do you think that we could maybe show some DPA screenshots so people can understand what this looks like?
Yeah, let's do that. So brought up a screen here of what would be a typical DPA webpage showing the wait time analysis along with the anomaly detection pieces. I like this screen specifically because we look at September 21st and it's got a higher column, but it's just about as high as September 24th and September 17th. But you see that the predictions for September 21st and first in the lower chart show that it's anomalous compared to previous days that are similar to it. So within its week, within its day of the week, it's strange compared to September 24th, which is more normal to be that high. Then you look at September 14th and it's way more anomalous than what it was. So here we see that what was expected is a lower bar, even though on other days it's expecting a bar just about as high.
So just so I make sure I'm clear, warning critical, that's deviations away from expected, or?
Yeah, exactly. So when we have the calculated standard deviation, by default we ship with 2 standard deviations being warning and 3 standard deviations being critical. So there you see the bars at the different heights for each individual day that we're showing here. And September 21st, you see that the critical bar is actually fairly narrow, which means that we have quite a small standard deviation. Whereas you look at September 15th and September 17th, that's got a wider range for the warning level, which means for those days, we're expecting a wider range of data.
And so just so people, and we all understand, when you say 3 deviations, I think that means 98% of the data is under a normal curve, which means that there's like a 2% chance that this would even be happening. So like this is the signal through the noise part. This is where somebody says, what should I be looking at on any given day? Well, that is what you should be looking at and investigating first, most likely.
Yeah, and of course we've made this configurable within Database Performance Analyzer so that if you find it's too noisy or not noisy enough, you can actually adjust these levels to be some multiple of standard deviation. So if you want less noise or more noise, you'd like to find out earlier when things are going wrong, then you're able to adjust those levels.
So that's great from a singular instance of a data model that's coming in. What are you doing to scale this model for the plethora of customers that you have to take advantage of this?
That's a great question. So the first thing that we did was we trained the model beforehand. So there's not a lot of compute necessary on the customer sites in order to run this. Because the model's going out mostly trained, there's not a lot of CPU cycles required on the customer side in order to handle that. Moreover, in order to retrain our data, we have a program called the SolarWinds Improvement Program, where the data actually gets reported back. And so we're able to see how many alerts are getting triggered, what kind of data is triggering the alerts, and what users are doing to their different thresholds to send back to us. And so we can have our data science team once again refine the algorithm so that as we continue to do future iterations and future releases, we'll be able to keep that scale low by maintaining the majority of the compute done here at SolarWinds.
And that's important, right? The success of your machine learning model is based on continuous learning. It can't be a stagnant, here's my template, I'm deploying this, and it's not going to be any changes. If you want to increase the accuracy that you have, the way to do it is exactly how you guys are doing it in respect to capturing the additional data in terms of the outcome that's continuously growing and having that run through the model itself to increase accuracy.
That's right, and we've already started to see that, right, with our customers already reporting back with our current releases. We're seeing that there's certain situations and certain data shapes that are not doing well with the predictions. And so what we're able to do is go back and say, all right, what parts of the algorithm are working well? And this is where even more machine learning is coming into place, is we're actually able to take parts of the algorithm and ignore them. And say, all right, that part of the algorithm isn't working so well. Let's toss that out and have the machine actually select which pieces of that seasonality are necessary and ignore other pieces. And it will say, all right, I need pieces 1 and 2, but I don't need piece 3. And so it's continually learning and giving us feedback as far as which pieces should be ignored. And that's, again, telling us that, okay, these are the more important pieces. Here's what's actually going to detect the anomaly. So with that feedback from the machines, we're actually able to learn how to refine the algorithm further without us even thinking about it.
Now, is this something, this type of machine learning that we built into DPA, is this something that we might see in other Orion platform products?
Absolutely. We're looking at it from a holistic perspective. The reason that we started with DPA is, one, we're answering that question of what's most valuable to our customers. How are we going to make sure that they have less alerts inside of their environment? That's our overall burning question. And app performance is everybody's number one concern. You don't want to have the slow website that's not able to serve your customers or serve your business. And what we decided to go with DPA first is because when you have a slow website, usually that can be due to slow database queries.
What?
That's usually because the hard drives are slow, right? It's never actually the database.
It's always the network.
But we're going for root cause analysis. So in order to give people a great accurate picture of at least eliminating the database as a possibility or pointing the finger at the database or something related to it, we're beginning that path towards root cause analysis. But as Database Performance Analyzer fits into our whole suite of products, there's going to be more that we add into the other products to say, are you having slowness on your network, or is it on your hard drive, or is it in your virtualization? Is it you're overloading CPU where you used to not be overloading CPU? So that's where we're going to start adding into our different products as well.
And the benefit of the activities that you've done in doing proper envisioning in terms of adding the machine learning aspect to your data model, you now have the ability to take those learnings to other data sets within your organization and use the same practices. What's most beneficial here is the fact that you've pinpointed the initial problem that you wanted to address. And it was something that you could do in a shorter period of time to have an upskilling of best practices around machine learning, and then taking that knowledge to the next step now and adding it to additional products down the road.
Right, yeah, because when we first started to think about machine learning, there was the old knee-jerk reaction.
Right.
Of, hey, what can machine learning?
Right.
Let's just go for it.
Slay all the dragons.
Just throw all of the data at it, and
Yeah.
just it will tell us what to do.
Right.
And that wasn't a great guiding principle when we sat back and thought about it more clearly. Like, what are we actually trying to do? What do IT professionals actually need? And by answering that question, we're much more equipped to actually analyze the right pieces of data and come up with solutions that are practical and real world.
And that's another part I want to call out too, and the fact that you actually had the conversations with different groups within the organization in terms of what matters to them most. A lot of times you'll see ML deployed for the sake of ML, the whole rubbing the AI on a solution, adding the unicorn to have that availability, and they don't take in consideration what the actual need is. And so the outcome is great, but it doesn't benefit anybody. And so there's no advantage of having it. It's just extra workload that was done for what, right? Having that conversation within an organization, whether it be internal or external, is very beneficial to ensure that the work that's being done in ML is actually going to move the needle for that organization.
So Microsoft actually has data sets that are similar to ours as we look at our data that we're gathering versus some of the sample data and workshops that you have at some of the Microsoft websites. We've been able to find a lot of close parallels and use your guys' tools in order to help us learn how to apply those different algorithms and those different batches of AI and machine learning to our specific data sets.
And a lot of the tools created that Microsoft puts forward for upskilling is based on the feedback from customers like yourselves that have inquired about, how do I accomplish this? How do I enable this? A lot of the tools are made available directly into your subscription. There's a new tool that we'll be showcasing later on, like Microsoft Learn, that actually uses a sandbox to actually test out your theories and follow steps to create labs or to complete labs for the outcome of X. And that's for upskilling in terms of what ML can actually do.
Yeah.
Would you like to show us some of that Microsoft Learn stuff?
Yeah, definitely.
Okay, time for a dozy-do.
Dozy-do. All right, so first tool we're going to show is the Microsoft Learn portal. What's great about this solution is it doesn't require your subscription to enable testing and lab completion. I pulled up the modules here for you so you actually can see the amount of modules that are here. There's currently 30, and this is growing. This is not something that's going to stay stagnant. It's going to be always evolving and changing because of the different models that are being made available through machine learning and through the Workbench capabilities. As you can see, some address specifically on the vertical side. So you'll see some insurance examples or financial examples or what have you. Some are more generalistic. There's different methods of input access as well. Some coming from IoT devices, some coming from data that's been historical or what have you. Again, what's great about this is it's a sandbox model. So when I go in and I want to complete these labs, it's completely free. There's no subscription required. You don't even require an Azure account to accomplish this. You do set up an identity inside of Microsoft for the enablement, so you're creating an Outlook.com account or use whatever email account that you want to generate for this solution. When you go through and you do the labs and you do the tests, once you've completed, it actually wipes the sandbox clean. So there's no residual of data, there's no leaking of data, it's all gone once you've upskilled and got the ideas to accomplish what you're trying to accomplish. The other thing that our team loves to do is we love to work and learn alongside customers, right? No one in our team is considered an expert. We're all lifelong learners, and we do that specifically, especially in the machine learning space, because of the fact that you're constantly learning. There's still so much more that we haven't even touched yet in regards to the amount of data and the patterns in the data that we can come across. So one of the great labs that we put together was with Toyota, where they came to us and said, hey, we have a plethora of data that we are trying to chew through and find out patterns in terms of part failure within our vehicles. And we spent 5 days with them, and we actually had an R coder come in and work on custom algorithms alongside them to have an understanding of what can we actually accomplish with all the data that's coming in to find those patterns to do predictability on a part failure in a vehicle to lessen the amount of recalls that happen on these vehicles. Now, a lot of the data obviously is proprietary and we're not able to share that out, but what was great was we were able to work with them to come out with another lab, specifically that's shareable, around pricing of vehicles. So if you can imagine when you're building a vehicle, so I'm releasing a net new vehicle to the general public, a lot of the challenge is what do we price it at to be something of interest for people to take a look at in terms of all the other choices that are out there. So what was great about this model is it actually takes into consideration what parts are you using in the vehicles, so the grade of the parts that are being used in the vehicles, how the assembly time of the vehicle itself, and then in comparison to the rest of the marketplace out there and the other vehicles that are out there. And the solution does its best analysis in terms of the learning that it's had thus far in terms of what you should price that specific vehicle out at. And you get to choose the parts that you're going to be using. You can have it 4-door, 2-door type of engine, what have you. And then it pulls up the analytics specifically to your geographical region. And that's the thing, right? There are so many different aspects of data that's available that you may not even consider out of the gate. And it grows along with you when you're building out your data models. My first instance into machine learning was actually by accident. I was on a project where we were working on taking a mousetrap and connecting it to a Raspberry Pi for the specific reason of SLA. So the time between the mousetrap being set off and the pest control company coming in and clearing out the trap. What we actually discovered was the data that we were actually capturing was actually also capturing the pattern of mice that were traveling through the building itself and where was the best places to put the mouse traps. So that was how I actually fell into machine learning by accident, trying to address the SLA problem. The data was showing us another pattern. And then taking that data to actually understand within 72 hours a large-scale warehouse where the mice were actually traveling through the warehouse at certain times of the day and where was the best places to put these mouse traps to catch more mice, right? A lot of times the data that you're receiving, you don't have the actual question you're trying to address, and the patterns that show you actually might bring up another question or opportunity that you're now can address with the data that's being brought forward. And that's why labs like these are so important, because you then get that understanding of how the patterns actually occur. And there's no barrier in terms of developer knowledge or language. I'm actually on the operations side. And so what's been amazing for me is that using the workbench that's made available here in Azure, it doesn't have a barrier of, okay, well, I got to code this in Python or Node.js or what have you. It's something where if I have the data sets and I have access to the data sets and then go through and deduce which algorithm is the best to use to find the pattern for this solution. What a great way to do it in terms of a lab and understanding of how the information gets digested for the outcome of X, whatever that may be.
Yeah, I've been using the Microsoft Learn and Microsoft Academy tools, earned a couple of certifications as well along the way. I love all the stuff that they provide for free, like your local library free. It's just wonderful. That about wraps it up for us here today. I want to thank Anthony and Karlo for joining me. My name is Thomas LaRock. Thanks for watching.